started. What we'll do this morning is this is design evaluation and model validation. We'll go through it. There probably will be questions here. And whenever this finishes, we'll take a break. That might not be the normal break time, and then we'll switch over, and then you're done listening to me for the most part, and Lucas takes over, which is good for everybody. So we'll jump into design evaluation. So just kind of really briefly or really high level, a lot of different, this is a word that's kind of an IEEE word that we've kind of propagated through the industry, but it means different things in different contexts and for different groups of stakeholders and things like that. So just generally speaking, you can kind of just consider it exactly how it sounds. It's you're evaluating the design of your facility. And I'm saying facility, I guess I wrote site here, but facility is important because when we talk about design evaluation for the rest of this morning, aside from the detour to validation, we're talking about design evaluation, we're talking about plant level only. So we're assuming the inverters are compatible with the performance requirements, and we're just going to test the plant as it's constructed to see if it actually has the right performance or has any issues and that kind of thing. So big key thing for design evaluation when since you're modeling your plant, your facility as a whole, similar to the rest of the discussion yesterday, you need to have validated equipment models, right? You need to have a verified plant model. So let's see if I have, okay, I think they're in a couple of slides, but validated and verified, or verification and validation are another set of words that we like to change the meaning of for this discussion specifically. So I think there's stuff on it later, but just generally validated, and the way I keep it straight in my mind is validating is when you're comparing measurements against something else, like a measurement to model or performance in a criteria. And verified is kind of when you're doing a paper exercise. So if I'm verifying a parameter, like ERCOT's parameter verification report. So I would verify a plant model by checking the voltage slopes and the frequency droops against the equipment and the model. I would validate the equipment model by running the tests in the test bench and testing the model against it. So those are two examples, really simple examples, but does those two words make sense for the rest of the discussion? If it gets confusing, just raise your hand. Because this is one of those things that like we spend a lot of time discussing and arguing in the IEEE world for, because we like to do that for a definition. So just a disclaimer here, I have been in, or I was and continue to be in a leadership role for the IEEE process for 2000 series. It's P2000 for now, but just for updates for everybody that's done, we got consensus on it with like a 94% consensus. And its editorial review is going to get published in the spring. So for those of you who are eagerly awaiting this 2000 best practice standard, it's coming finally. And what this does is it's not a standard, but it's a recommended best practice is what the IEEE calls it. And basically the process would be you would look at the requirements in IEEE 2800, 2022, the base standard, and then use this .2 best practice document to basically show you best practices, how to verify conformance with the base standard. So I apologize for being the subgroup who slowed this thing down for probably 18 months or 12 months. But you'll see in the validation and evaluation discussions why this is such a contentious topic and why it took us 18 months to end where we started. But that brings me to the disclaimer here. Because I was involved, I have a lot of feelings about it. When you do a consensus collaborative type of process, you make compromises with people. So because of that, my opinions that you'll hear maybe today might not match exactly what's in the document that comes out. In those cases, those are the arguments I lost, but I still like my opinion. So you'll hear what I want to say today. If you want to hear the consensus, you see the consensus stuff, the drafts. That's my disclaimer. But thank you to everyone who was involved in the process. For those who balloted and voted or kept submitted comments, our subgroup was specifically design evaluation and model validation came first, but it's kind of loose in between there. So thanks to everyone who participated, and that's what's coming. So just generally, this is kind of these are slides from IEEE that we just reuse for this discussion, but this whole process is what we are calling a conformity assessment. So conformity is a very important word again. You'll notice words are very important in the IEEE world. But this is a conformity assessment. So these are conformity steps in 2000.2. And when we say conformity, we're saying to show conformance with the base standard requirements. So when we say conformity today, it means checking against the requirements in the document or another document. So it's very important to understand conformity with 2022, the base standard, does not mean you're grid stable. Just full stop. That is a really big misconception in the standard. Even with the folks who are involved in the standard drafting process for, 5 years now, since we've been started, or maybe earlier, since we started the base standard. But conformance with IEEE 2000 does not mean you're grid stable. What it does mean is helps conformance with 2000 gets you to a better starting place than without doing this conformity assessment and without using the principles, right? So the example I like to use is without the conformity assessment and you want to build a house, you go and you chop down a tree and you have to make it into lumber that's the right size and you use that lumber to build your house, right? IEEE 2000, you start with the lumber, right? They've standardized the lumber sizes. You know what you're getting. You might have to cut some of them or measure them differently. We'll measure them and then cut them. But you're starting with a better place, right? You don't have to do all the extra legwork of going and cutting down a tree. You already have a standardized set of lumber. So not going to solve every single problem right off the bat by conforming with 2000, but it's a really good start. And just I'm saying that just because for those folks in the room who have the leverage or who may have parts of those discussions at your own companies, when you talk about adoption of 2000, the base standard, it's important to know that you need to understand what's in the standard and why it's there and the limitations of what's there. And I'm going to say this, but I'm going to preface what I'm going to say with, we would love everyone to adopt as much of IEEE 2000 as possible, but do it in a thoughtful way. Just copying and pasting requirements into your own documents without knowing what they are might not be a good decision. I feel a lot of those calls where, developers says, well, the utility put a transient overvoltage requirement just like the base standard in there. How do we test and determine that? Well, unfortunately, transient overvoltage is one of the two, in my opinion, three maybe major flaws of the base standard. We should never have had a transient overvoltage requirement in there because you can't test for it, really. You can't meaningfully test for it. The other kind of two that get confusing are consecutive ride-throughs. And there was a mistake that I missed in the base standard for reactive power for type 4 wind. But the other one for consecutive faults was one of those things where we got really ambitious in the base standard. We put it in there as a problem. And when you get to the point of, well, I need to actually implement this and hold someone to these requirements, how do you prove that, right? There's consecutive faults are in a model, but they're just a counter, right? So for those of you who just are curious about the consecutive faults, really the intent is to say if there's a bunch of reclosing or a bunch of similar or close by faults that if you get hot, your converter gets, or your chopper circuit gets hot, or other things get, temperature rise, that you trip offline because of that. But models, even the EMT models, don't have thermal things in there. So it's one of those situations where really happy that you adopted parts of 2000, but that also caused a lot of problems because then how do you test without understanding? So just keep that in mind that 2000 is a kind of good starting point and a tool to use, just like automation, just like the EMT and the modeling tools, is a tool to get you where you're going. But it's important to know what's in there and why. And it's hard, I guess, from my side, because I've been in all the discussions. And a lot of the times we will say, if we can't agree here or we can't understand each other in the drafting team, then how can we expect industry to understand? So there's definitely a gap in understanding and training on the base standards for 2000 and the 2000.2, but they're still really good documents and they still really help. So that's my preamble on the base standard and the process, but what was that, a tangent on conformity? Yeah, okay. So this is the conformity assessment process. And you'll see the dotted line. I'm pretty much going to talk about everything to the left of the dotted line. After planned construction is complete, then you're in the NERC standard world. You're a NERC registered entity at that point. There's stuff you could be doing or should be doing to test your stuff, test your equipment afterwards. But we're going to focus on the pre-commissioning stuff today. So just to kind of highlight the post-commissioning things real quick, just so we know what comes next. And part of this was we wanted to put a few kind of really stringent verification, not really stringent, but a few quantitative, qualitative verifications after commissioning to put a little fear into, the people doing the process that, hey, something's coming for verification, so don't cheat your commissioning or do your modeling the right way, which is much, much more difficultly done than said. So the other piece is commissioning tests, actually testing at commissioning. ERCOT does a good job of this. You're not going to do a fault test at commissioning, but, doing a ramp for your reactive power is great. Doing a small voltage set point change is great. Feeding a fake frequency in is a good idea. They're not going to test every single control scheme, right? You're not going to fix everything, but if someone gets one of those 3 easy tests wrong or 4 easy tests wrong, it's a pretty good indicator that the rest of it needs to get some evaluation. So the other kind of things are post-commissioning model validation. It goes along with testing. That looks a lot like what NERC Mod 26 and Mod 27, which is just Mod 26 now would be. I think post-commission monitoring is just, if there's an event, get the data and run it, which is like a really optimistic process, but it's in there. And then periodic tests and verifications through the lifetime of the plant, which all makes sense, but could be very difficult to implement in the regulatory sphere. But this is a good place if you want to have your own requirements or look to see what it takes to do these types of things, to go in and check out that language once it gets published. So that's it for preamble on the things we're not going to talk about. But so we'll talk about the design evaluation pieces today. So the actual design evaluation pieces are the red boxes. IBR unit model validation, plant model development, we talked about yesterday. Model validation and design evaluation we'll talk about together today. So I did go out of order, but it should make sense. The other thing to kind of lead us into, did I do type testing? Yeah, so talk about type testing real quick. So type testing is lab or field tests. We talked about it a little bit yesterday. And this is basically taking your product, putting it into the lab or in the field, probably the lab, and just cranking it around. You're doing really strong faults. You're doing big phase angle changes, deep faults, long faults, unbalanced faults. Essentially, it's a data person's dream, right? You're just doing all of this stuff to get data from the type tests, and then you use that data throughout the process for model validation, checking in, and that kind of stuff. So for model validation on the unit side, we talked a little bit in the other course about hardware in the loop and control hardware in the loop. I'm not going to go into it again here, but just for everyone in mind, there's different ways to type test and different benefits of each. The probably more accurate, and someone can correct me if you don't agree with me, but I think the most accurate way is just a straight up hardware in the loop type of test bench. And that is literally taking your hardware, putting it into the lab and running things on the actual hardware, which is much easier for some technologies than others. But that's probably the best way to do it. We talked about yesterday that those labs are hard to book, and there's not that many of them, and all the major OEMs use them. So they're booked out for a couple of years at a time, and you only get a certain amount of time. So you're not always going to be able to do a hardware in the loop. Most major OEMs do a hardware in the loop, but you're probably not going to do it again on the same equipment. So there's other ways to do it, and there's things like control hardware in the loop, which is kind of somewhere right between a hardware in the loop and an EMT test. You're putting the controllers into a test bench and testing the controllers. So it's a little bit different, but it's still a good way. So those are the 2 ways you would type test. We're going to stop talking type tests for now, but what that does is just gives you a mountain of data that you're using to do other things. So it's not just the traces and the P and the Q and the V, the voltage and the power and the reactive power that you're getting, that you're measuring. When you're doing this unit level, inverter level hardware and tests like this, you're looking at everything, right? It's you're recording exactly the profile that you played into. You're recording exactly the parameters and exactly the conditions and measurement errors, and you're getting back from the actual product, much more stuff that we'll never see as end users, like flags of faults, or did you enter a mode or not, and things like that. So those are used on the back end by the OEMs to validate their models. But what we also want to do is kind of give some trust to the industry that the models that you're giving me are valid and are accurate. So without a model validation test that someone's letterhead is on with a lot of plots and a lot of comparison, we're basically just trusting the manufacturers to take at their word, right? We're just saying, yep, this is what it looks like, which is not a great way to make sure everything's reliable, in my opinion. So what I recommended in kind of the design evaluation piece and the IEEE and the NERC world is that this falls onto the manufacturer, right? If you want to give me a good model, if you want to give me a detailed model and you want me to use it, give me a model validation report, which softens the blow a little bit for developers and transition service operators, because when you start talking about 1,000-page report of parameters that you got to check differences between, no one has time for that. But this is something that's done at the manufacturer level already. That's done already, right? So it's literally just a difference of, I've taken my test, I'm going to take out my really sensitive IP. Maybe that's a certain test that shows a weird capability someone can use. And I'm making into a kind of a readable format, like we showed examples of yesterday. And I'm giving you this as part of the model package. That was a recommendation we made at NERC. That's what some manufacturers do and others do in varying levels of success. So very important as a very root cause of model validation is to have the valid models validated against the actual measurements. So those are the building blocks, are the validated unit models. And that's using that massive thing of data, and you're doing your EMT model against it. And that's the kind of source of truth we talked about yesterday. So this is the starting point for everything. This is a very important step. It's a very important thing to make sure that you're getting from your manufacturer or your developer who's going to get it from the manufacturer. And this is a place where don't be afraid to make a requirement to do it for your side, because you're not going to do the work. You're just going to get a great report at the end of it. So once you have the validated unit models, you have to build, like we talked about yesterday, the plant model, put them all together. You take the validated building blocks and put them into a plant model. I guess the only thing I missed was this says unit level hardware tests. It doesn't just mean inverter. I may have said that. It also should be the plant controllers as well. But the plant controllers are probably always going to be a control hardware in the loop. It's really not a huge reason to do a full hardware loop for a plant controller. It's just a controller. It's not doing much else. So that's a perfectly fine control hardware in the loop thing. And that was actually a very contentious piece in the IEEE process, was do you actually validate and type test a plant controller? And the answer was, that sounds like a good idea, but no one wants to write it. So I wrote that section because I thought it was important, because it's half or more of the plant's operation. You're much more often operating in an operating point with the plant controllers in full control than you are in any fault right through mode, just over the lifetime of the facility. So it's very important for the plant controller to be validated as well. So when it says validated unit models, it's it could be the inverter, or it will be the inverter, it will be the plant controller. If you want to go crazy, it could be the SVCs or other switching controls, but those are usually smaller OEMs who don't always do this huge type testing. So you might have troubles getting that type of data from them. So what you're building, yes.
The power plant controller is validated individually and the inverter individually as well. What's your take on that?
That's an argument I lost. That was the consensus that we got to. So validating them separately is okay, right? Because at the end of the day, with the communication between the inverter and the plant controller is doing all the math and it's sending a current command to the inverter, right? So we'll catch a lot of everything, right? So it's fine. It's a really good step in the right direction. I like to do them both at the same time. You will be doing both at the same time in the design evaluation, so you're not missing it. But there's a lot of just concern about setting up that test. And there's a lot of concern about the extra value it brought, right? And my take is the value is that you catch those handoff issues. Because there's certain things that a plant controller can do to just get out of the way of the inverters during the fault. And really studying the handoff and how it comes back into peak power plant controller control and the windups and any sort of like weird behaviors is, I think, really important. But I lost that argument, right? So there is value. It probably isn't, to be very honest, it's probably not a lot of value, but you're doing it anyway. So just do them both at the same time, is my opinion. But you will do it when you put it together in the design evaluation model. Any other questions? before we move on to the other half of the slide. Yeah, go ahead.
Yeah, so when you ask for the benchmark of the validation report, is there a list of, that's a standardized list of tests you want to see covered in that report?
So there is a standardized list. The one that's in IEEE 2000.2 shows that, and that would be subclass 5. Subclass 5 is type testing, 6 is model validation, 7 is design evaluation. It's not exhaustive, but it's pretty much a standard subset of tests that we're saying you must provide that will give you the data you need to validate the things that you need to test for conformance with the base standard, which is a really horrible sentence, right? So it's not exhaustive. I think more type tests are always good because, like, at the manufacturer level, they're doing 1,000 of these tests, and we're asking, I don't know, remember what it was, like 20 or 30 tests in the IEEE. So that's like the small subset list, and that's a good place to start. And that's things like fault ride-throughs and our different fault levels and some just control schemes and ride-through modes and that kind of stuff. So for all intents and purposes, it should cover what you're going to do from that side. So that's a good place to start. And again, that's published probably in spring, January, February. Any other questions on model validation before we go right to actual design evaluation? Okay. So we talked yesterday, building them together, you put them together. But then next comes verifying and testing your models. Verifying, again, is more like a paper exercise. That's when you've got your plant controller in there, it's connected to your unit models, you've got the collector systems and the transformers in there. And now I talk to my utility and say, hey, how do you want me to control voltage? And they give me an answer, hopefully. And then I ask, how do you want me to control frequency and primary frequency response? And there's probably an answer to that as well. And then that's a good starting point, right? Because again, we're talking about conformance with the base standard requirements. So at this point, if you're doing like a straight up pure design evaluation, you probably don't need the system strengths and things like that, or system impedance. If you want to kind of save yourself some work later, it's a good time to ask that, because there's a very possible scenario where you're perfect IEEE 2000 conforming or perfectly conforming with your utility, like ERCOT's assessment, and you're still grid unstable. So it depends on, you'll see the flow chart at the end, but it depends on what you want to do and how you want to how your risk assessment is. If you want to save some time at the end for probably a restudy, then maybe you just take those base values and pop them in your model and do the test, and then tweak it for a special tuning at the end. But that's also fine, right? Because if you do this design evaluation right, it's the same logic steps as doing the great model validation and switching parameters for your real site. So even if you do, without a weak grid tuning design evaluation for your plant model, you can be pretty sure that if I tweak some parameters for weak grid, that I'll probably still have a good match model. Again, outside of bugs and hot fixes and stuff like that. So once you put it together, you have your plant model tests. We'll talk about what those plant models are, but we're talking about doing them both in EMT and PSPD, which that's IEEE Minimum State on their language there. So do them in both, compare them in both, or compare both together. And then your utility knows, or the people you're giving the models to, or your design evaluation report to, which again comes from probably the manufacturer or the developer or a combination of both, then you know what model you should probably use, right? So it's much different for me when I was at a manufacturer or me when I was at a consultant to say, hey, emission service operator, you really got to use this user-defined model. It's really accurate. Trust me, right? And then they say, no, our rules are PSPD only. But it's a lot different to show them a 100-page, that's probably too many pages, like a 50 test benchmark plant model design evaluation report that shows massive difference between the two models. Then they have to think about it some more, right? Because then it's, am I okay with a 20% error? Am I okay with a model that may trip offline for some stuff where the real plant wouldn't? But then they know, then they can make an informed decision that's not just trust me, please. So very important to do the tests in both domains where possible or where appropriate and benchmark them together. And that's a big caveat because not everything should be done in both. Not everything can be done in both. This is very important. So the end of it, the whole end of the validation kind of in building process is benchmark plant models. That's what you want, is a benchmark plant model between the two. And then you put it through a bunch of stuff. So I guess your question was early, and I forgot that I put this in here. So these are the tests that are in the type. This is subclause 5. These are some of the tests that are in there. So voltage and reactive power modes makes sense. Primary frequency response makes sense. FFR is weird in the US. It's wide use in Canada. Voltage disturbance right through, frequency disturbance right through. Those both have, the voltage has both performance and right through capability criteria. Frequency has just stay online, basically. Limitations of overvoltage for over one fundamental frequency period. Power plant controller testing, which was crammed at the end because I wanted it in there. Frequency scanning, and then protections. So frequency protection, roll call protection, voltage protection, AC overcurrent, and unintentional islanding. So you'll notice that kind of for 5.15, very similar to the NERC disturbance reports. Some of these you can't do in PSPD, straight up, right? Again, another use case where you probably are doing a joint mixed co-simulation or co-domain simulation there. What are the challenges? And these are where I'll have a lot of thoughts because of the second sub-bullet, right? Which is it's really hard to get consensus on this. Extremely hard to get consensus on this. And this, I was joking a little bit earlier, but this was literally a 12-month discussion. My defense is we had the hardest group because the design evaluation is very touchy. This was literally 20 of us arguing for a year for consensus on what to do and what's acceptable as a match. And the consensus was provide no input whatsoever in the base or in the .2. So that was something that was removed during the last comment period. We had an informative annex that was it wasn't a requirement language, but it was guidance. So it would say they had a survey with the manufacturers, but basically said, here are the ranges of accuracy that we have out there right now. So if you're making a requirement and you're picking a quantitative match type process, here's what you can go off of as guidance. So that's what we had in there. It's not in there anymore. We trying to put some of that into, there's a NERC model benchmarking and validation white paper coming out that I started before I left NERC, and they're finishing it up on their own, but some of the language is in there too. So you'll see some of that come out and be public for help when we're trying to figure this out all together. But the big piece and why consensus is really hard is two pieces. Is one, there's a fear because of what happened with the base standard that people just copy paste stuff out of .2 into their requirements. And even if it's in an informative annex and I have a table that says models must be 1% accurate, that's too accurate. But if I say a model must be 1% accurate, even if it's an informative annex, someone could literally just copy that into their interconnection agreement. And that's a major problem. So that was one of the main fears and reasons why a lot of detail got removed. The other piece, and somewhat related to the first one, is the manufacturers have really different modeling standards. So we talked about, I guess, yesterday morning, user-defined models were very bad 10 years ago. Some manufacturers who were kind of prominent in the markets that were really heightening their requirements may have made decisions that will help in the future, right? So some may have gone to full code integration or really detailed block diagrams or parameter mapping. Others didn't, which means there are certain situations, especially in the extreme fault tests, where they may have a pretty good model otherwise, but they're on an error that's just outside of what we agreed to. So between that very different standard and modeling and quality and accuracy, plus the fear of it becoming a real mandatory standard. And because also part of IEEE is there's bands for how wrong your measurement can be. If you add all those things together, some of the manufacturers who were polled, which is perfectly fine, decided that they would take the conservative approach. They would say, well, I can't agree to anything better than 30% accuracy, which is not good. 30%, if you 30% accuracy, don't even run your study, right? My opinion. But I think it's true. That's just not acceptable in the world of a critical safety rule. So the values range from about 5% to 30%. And I've seen models that can do, for multiple OEMs, that can do very good matches for a lot of tests. But there's a big variance, and it's hard to have this consensus. We usually get away from this discussion at IEEE will because it's voluntary, but because so many folks just copy and paste it in, it's kind of the NERC mindset's bled into the IEEE process, and now we're actually, in people's minds, we're debating a mandatory enforceable standard, even though IEEE is voluntary stuff. So that was a big piece here. The other big pieces were, how do you actually calculate the error? And where do you calculate the error is very important, because it's one thing to say you must be 2% accurate, 3% accurate. What does that mean? Is it 2% at the beginning, steady state? Is it 2% at the end, steady state? Maybe that's fine for everybody. You can do that. Is it 2% during the fast transient piece, just post fault? That's going to be tough. So other areas have said, you get X number of samples outside the error range to cover those types of things. But again, it's just really hard, and we couldn't get consensus on how to actually calculate error, which kind of fed into the other discussions and all resulted in a really long discussion that got no content into the standard. So but that's also a very important piece is for the validation differences, the difference in the accuracies there, is it real or not? So while you're trying to, you would say when you're doing an actual test bench, the first thing you do is make the measurements accurate. That's like your very first step in setting up a test. Theoretically, they could all add up to something like 10% of just measurement error plus the model error. So then it's hard to say, yeah, my model's 5% accurate, but the measurement was 50% wrong. So just a big kind of circular discussion of capabilities and standards, and it just ended up with no consensus. So my opinion is to go quantitative with a qualitative check, and I think I talk about it. Yes, great. Bit of pacing here, I guess. So the big thing, quantitative, qualitative. So for quantitative, for folks who don't do model validation, or this is one of those also, yes, these words mean what they're supposed to mean. These are actually not redefined for IEEE, but quantitative and qualitative, probably the most contentious issue in the design evaluation subgroup outside of the aggregation discussion that I also started the argument about. But besides that, qualitative, quantitative, huge contentious point. And this goes back to something I think I said yesterday, which is the IEEE group is very diverse in career experience and really high quality experts. So there is this big kind of mindset and discussion between how prescriptive is too prescriptive and how much informational guidance is too much, right? So there are folks who had, like I said yesterday, who had a really good mentorship, who would say, well, I don't need this IEEE standard to tell me how to validate my model, what a good model looks like, because I had a mentor who taught me that throughout, right? That's great. Other people didn't, right? So this was or can be still in future revisions, perhaps an opportunity to build engineering judgment through informative language in the IEEE standard, because you need some sort of guidance for these types of requirements, right? That's a huge kind of sticky point in the regulatory industry or regulatory side of the industry is, I want to do something, I know I need to do something, but I don't have the experts in my shop to actually put numbers to a requirement. So I'm going to look somewhere else or look for guidance. And a lot of times looking somewhere else, looking for guidance is really difficult to do. And then you don't do a requirement, right? So the quantitative piece here could go a long way to informing those things, but we couldn't agree on what quantitative means. We even tried to do like a mixed approach, right? You do a quantitative, if it passes that, then it's a screening basically. Anything outside the bands, you would explain it. Anything weird, you would explain it. Weird is the technical term. So the pros of quantitative stuff, quantitative assessments and model validation is you can standardize model quality, help standardize model quality. If you say you must be 10% accurate or you're not interconnecting, now every model is 10% accurate. Standardizes it pretty well. It automates screening. So for those who hate doing tests and love automation, you can automate parts of this. You're probably going to automate parts of most of the model validation piece anyway. But this will cut down a detailed review of 1,000 plots to maybe 10, because those are the ones that are outside the bands. But it also informs engineering judgment, which we just talked about. The con is the big fear, which is totally reasonable, is if you make the wrong error bands, you're going to overly constrain good models and you're going to really slow down interconnection. This is for a large load example. I think who was they're a Canadian, right? They put large load requirements in, but they had a very strict load variance requirement, which essentially means no one's going to connect. No one can meet that small percent of load variance. Maybe that was intentional, maybe it wasn't, but the end result was here's a load smoothing criteria that no one can meet, which means no interconnections, right? If you say with your model validation, 2% model, you're probably not going to get that from anybody, which means no one's going to connect. So it's really important to have some judgment and know what's out there and how to do it and how it works so that you don't overly constrain everything. So the other con is this: if you do just a pure quantitative, you can fall really easily into automation traps, right? You can just really easily just press run. If I go through and it checks everything, then if everything's inside the bands, I'm just going to pass it on. It's validated, right? But there are a lot of behaviors that could be within an error band that are wrong, right? If you have a 5% oscillation right inside the error band, that's still bad performance, but it's technically within the math of the error calculation, right? So very important to have to both components there. So qualitative, on the other side, people who do this all the time love qualitative stuff because they get to use their judgment. They don't need a checklist to tell them what looks good or what doesn't look good. And they like to have the freedom to actually look at the model performance and ask those nuanced questions that you may miss if you automate everything or do quantitative only. So if you do this really well, if everyone doing a qualitative model validation is like been modeling for 5 years or so, and they really know what they're talking about, it really could be extremely helpful for everybody involved in the process, because they're going to see the things that are wrong that the script won't see. And I've had experience doing this on both sides of the fence, and I've had people do it to me as well. Like, and a consultant, you do a model validation quick or do some tests, and you say, well, this looks weird. It's kind of right, but it looks weird. And the manufacturer says, yep, that's a bug. Or I'll be at the manufacturer side and I'll give it to ERCOT, and ERCOT says, this technically passes their requirement, but I'm really curious about this piece of your response. And then I say, oops, and then we fix the bug or fix the performance issue. So it can be a really good tool, but it requires a lot of experience, and mixing the both again can help there. So the con here is there aren't enough of those people around. Not even close. Basically, you would need everyone you talk to at all the utilities who do the model work to have this type of knowledge, which is not the current paradigm right now. So it's also really hard to automate. How do you automate engineering judgment? Hard to do. Maybe you can. Maybe you're making your own tools to help you out. But what that means is you're doing this all by hand. And if I'm an experienced engineer, I don't want to spend my entire day reading benchmark reports, right? That's going to lead me to fatigue and I'm going to miss stuff. So that's another kind of negative to it. But it also doesn't help standardize anything. So that can be also very difficult, especially for the developers and the manufacturers, because if you don't standardize anything, if you just say everyone decides what acceptable means, then you can have, New York accepts the model that's 30% wrong. Texas accepts the model, won't accept it unless it's 10% accurate. You may also have, if it's a judgment call, and this happens a lot of times in different interconnections, is I'll submit the same exact performance, same product, very, very similar performance, 2 days apart. One passes and one doesn't. And that's the risk of qualitative without guidance. It's engineering judgment, right? And everyone's engineering judgment is different. So that can be very risky for developers as well, right? They could say, I'm going to use this product because its manufacturer is great, their models are great, their performance is always good, and they submit the same performance or very similar performance for different projects, and now one's on time and one's pushed back 6 months because of qualitative assessment. So not a huge knock on it, but I'm saying qualitative is important, just not as the whole thing. So I took out Andrew's words from this document. Andrew said, this is my preferred. but I'll say it out loud. So this is what we kind of tried to do to make everybody happy for this. So this is what I think is a really good compromise, right? So we said, and for attribute world, should and shall obviously have differences, just like the compliance world. But what we're saying is you're going to do the unit model validation, unit model simulation results tests, and the type testings. You're going to do that anyway, right? That's why it's in the dotted box. That's subclass 5. We're taking that into subclass 6 and 7. When you have the measurements and you have the model performance, the first thing you got to do is calculate errors based on whatever method you choose. There's a bunch of them out there, a bunch of velocities out there that can be automated, right? If all you're doing is taking samples and comparing them with what you expected and calculating an error, that can be automated. And then plotting those error bands around the measurements, again, automated. And that would be the typical errors that we had in what used to be Annex H, which is gone now completely. So basically the first step was you're doing the type test already, you take all the data, you have a tool that just puts error bands on it, and then you can see just one plot with the error bands, the measured response and the model response. So it helps me both do the qualitative assessment at the end and also helps automate and show me kind of screening at the front end. So after you have those, that's the should. So that's the quantitative piece, that's the should. So that was a strong recommendation basically in the IEEE world. It basically goes may, should, shall. May is, you do it if you want. Should is you probably should do it, and shall is you must do it for conformance. So once you do the should, the quantitative piece, then you have those that produces the model validation reports and then the qualitative assessment. So basically it's do some math screening, automated math screening, then use your eyes and judgment at the end. That was our kind of consensus, or that was our attempt at getting consensus. This still ends with a validated unit model report, which is great, but just a little extra guidance and information for the. This work should go to the manufacturer. You don't have to do this. Developers probably shouldn't do this because this is the units. This is the PPCs. This is the inverters. But your developers don't know the details for these things, and they don't need to really. You just get this, and then you're sure about what you're having. So the manufacturers can do this. They, in their processes, use both quantitative and qualitative methods already. And then you just provide a review for any oddities or weird stuff. So this would also lower the burden on a lot of industry stakeholders, especially the service operators and things like that, because if they have a unit model validation report and they know that the model should work right, and they get a model that looks weird or doesn't look similar, then you just punt it back to the developer who's going to punt it back to the manufacturer, and then you have it fixed within your timeline. So it lowers a lot of the burden because a lot of this is kind of a piecemeal by people who want to do it in the industry, like just to check. Like I used to do this on my own just to check to see what I was using. You can push it to the manufacturer, get it early in the process, and it should lower the burden and lower retesting, lower extra steps. So the validation reports, again, really should only be done by the equipment level experts, but that's also good for us. We don't have to worry about it. So that's unit model validation. Any questions on unit model validation before we go into the actual design evaluation of the plant?
Qualitative, you were kind of saying mentor versus not having a mentor was kind of the delineation of how people could determine that. Could guidance on the qualitative be added into the, like, this is what a mentor would tell someone to look at?
Great question. Yeah, that's what we, so it's hard to write stuff like that in an IEEE document just because of the way that they have to be written. We attempted to do that though, by having informational quantitative requirements, right? So we tried to include informational quantitative requirements because then that's what you should expect or can expect. And if I read that, then I built that judgment. So we tried to include it, but the fear was there that having those in the IEEE document could risk just copy paste into a tariff.
Right, but you could say things like look for oscillations in
But
band and things like that, or
you could, yeah.
Values. That's kind of what I'm saying. Mentor doesn't have to say it has to be this value.
Yep.
They can say this is the wave short.
Yep, so there,
Wave shape this unacceptable or something like that.
yeah, so there's, when we go to design evaluation, the design evaluation piece, there's stuff in there like that, because our performance requirements for the plant. On the unit model validation side, we struggled to get any consensus for guidance. Because the general consensus, maybe because a lot of the IEEE experts are been in the industry for a while and they are really good at they forgot what it's like to be a new engineer in the world right now. A lot of pushback against extra guidance. The refrain was use judgment. Engineers have judgment, use their judgment. Something that ESIC we're trying to do is kind of help inform that as well. But it's difficult to give guidance without coming off as overly prescriptive for a requirement. So it's just a struggle we had while developing the standard. And my opinion is we missed an opportunity to do it. But that's part of the consensus process. Any other questions on model validation, unit model validation? All right. I did this already. Oh, we'll do it again because we didn't talk about compatibility. So we start. This is another weird nuance because we're kind of mixing and matching things. And this is something that is very important when we talk about making requirements or putting requirements on our systems or our products is where do the performance requirements take place? Where are you checking conformance with those performance requirements? Is it the point of interconnection? Is it the inverter level? Or somewhere in between? It's probably one of the other two, one of the two, right? So there's pros and cons to both, right? If I do a plant level requirement, the transmission system operators don't need to care what's inside the plant. They just say, give me a plant that does this. I'm going to check your plant against this. If it doesn't match, you don't get interconnected. Easier, less burden on the transmission system operator and the developers in that sense, right? More work for the manufacturer in that sense, because the manufacturers don't control the balance of plant. And if I have one piece of equipment, there's a bunch of stuff in between. I can't guarantee you, the developer or plant builder or owner or whatever, I can't guarantee you that the stuff in between is not going to mess up my ability to conform with the standard. So the other way to do it is to have an equipment level standard and requirement, which means that's basically like UL testing for regular electronics, right? It's like your equipment at the equipment terminal needs to do this with this capability. That's really easy for the manufacturer because then they can literally just say, here's my control, what I have in my control. I can measure at my own interface point that I also control. There's nothing in between. I can really easily say, this inverter is IEEE 2000 conforming. But that's not what we did for IEEE 2000. It's a plant level standard, plant level performance, which I think is the best way in the current industry because informing the plant performance, I think helps to not overly constrain stuff. It helps the transmission planning people to know what they're getting. And it just simplifies a lot of stuff. But what that means is that if you're a developer, you probably have heard or seen letterheads from your manufacturers. Then you ask them the question, is this a 2000 conforming or compliant inverter? But they'd say, no, this is a 2000 compatible inverter, which means basically, if you don't mess up your balance of plant, this will be just fine, is the kind of easy term there. So when we talk about compatibility, this is the design equipment to support the conformity. So this is the actual equipment level who, if treated right, can do 2000 things. Conformity is adherence to voluntary industry standards, right? So conformity, you would be conformant with IEEE standard. Compliance is mandatory. So you're conformant with you're conforming with an IEEE standard, but you would be compliant if it was an NERC standard. So just terminology break. And for those of you who really want to be in the know for IEEE words, we're not using the word conformance anymore. We're not using it, it's just depreciated. I don't know how you depreciate the term, but we did that with conformance. So we're just saying conformity. And again, in red on the bottom, it does not ensure grid stability. right? Conformity just says you're conforming with the voluntary stuff, does not mean you're stable on the system. Very important. So, who asked yesterday what tests we should run? Someone did. There's a bunch of slides of these, so get ready for a list of tests. So I'm not going to read out most of them, or maybe we don't do. But the big important piece is the first column, where the requirements applying. So in the IEEE rule, we're calling them the reference points of applicability. So where is the standard, or where is the performance requirement applicable? Most of the time, for these, for this thing here, this table here, this clause 4, a lot of these are point of measurement. And for those who don't know what point of measurement and point of connection mean, they're different than point of interconnection, like NERC uses. But POM is basically the inverter terminal. The measurement, point of measurement at the inverter terminal. POC is point of connection. So what you would call point of interconnection. So these ones on this table, these are, most of them are actual equipment level, equipment tests and requirements. So, so measurements, control capability requirements, executing a mode and parameter changes, ramping, prioritization of responses, that's probably a control parameter, isolation devices, re-entering service, the inverter is coming back into service after disturbance, interconnection integrity, which is a little loose, and integration with grounding. So those are equipment test, conformity. So those are point of measurement applicable. You'll notice 4.9 for inadvertent energization of the transition system. That's both. You want to make sure that the equipment's doing the right thing, and also the plant isn't re-energizing. So that one's at both. So I guess you can ask questions throughout. So those are mostly the plant, or sorry, the equipment level ones. I don't think the rest of them are equipment level. So any questions on these equipment level tests? These make sense to folks. Is anything? I guess it's too late now. We put it in the provision, but is there anything missing? Bearing off the front. All right. To the plant level ones. So these are the ones where a lot of us are probably more familiar with. We'll talk about testing a facility. And you notice that most of these are POM, especially the voltage and reactive powers. We have POC for the frequency response and the fast frequency response, just because frequency at the POI is about the same as frequency at the inverter terminal. So we put them at both. They're both related. So there's another small opportunity for me to express my opinion here for reactive power capability and voltage reactive power modes. Reactive power capability, extremely important to test, especially in the full plant model. And this is one of those cases where, I know this is an EMT course, but this is one of the few cases where I was able to get someone to put the word disaggregated in to the table, because this is extremely important for a lot of manufacturers to do this disaggregated. We've done this, or I have done this in EMT with partial equivalent, like you mentioned yesterday. We modeled the longest feeder. So why is it, in my opinion, why is it extremely important for reactive power capability to be done disaggregate in a model space with the full plant? Pretty much just for wind, basically. Because what happens is, especially on the inductive side, when you try to design a plant to meet a power factor requirement to capacitive, you're kind of really struggling to get there, to get to your 9.5 power factor. On the inductive side, you're usually blowing past 9.5 power factor, and you have a lot more capability, because it's especially at wind, because it's inductive plus the losses. And what that can do is really drop your voltage at the lower, or at the farther inverters, at the farther turbines. So what you can happen, and what happens, and why ERCOT's, I think it's Schedule 3 testing for reactive power testing is really important, is you do that, that's the test you can do in the real world. So I can test it on the real plant. So they send a signal, basically just give me your maximum reactive power capability, and sometimes stuff trips off. Sometimes the end turbines trip off, and then you have to basically recreate that problem in this disaggregated model, or whatever the most detail you can get, and try to mitigate those things, right? So that can be an inverter control to not push themselves out of voltage range. It could be retapping GSUs, the little taps on little step-up transformers, randomly, not randomly, but differently in different places around the plant to keep things about right. But why does it affect reactive power capability? Is that a lot of inverters have voltage dependent capabilities, right? So it's not just this gives me X megabars at all power levels or all voltages. It could be a value between 0.95 and 1.05 per unit voltage, and it kind of may derate outside of that range. And if you're in a wind farm, and you're probably going to get outside of 1.05 in a lot of places, or vice versa, or either or. On the low side, you're probably going to get lower than 0.95 voltage at your farthest turbine, which means summing up all of the reactive power capabilities, even including losses, you're not going to get the right answer, right? So it's very important for disaggregated. I think the note in there, the extra section was disaggregated, but here's a bunch of language I had to write to basically say do it at your own risk, because there's a lot of perceived extra work for disaggregated model building. So is there really? Maybe not. Most of the time when how do you build an aggregated model? You build a disaggregated model first, most of the time in some manner, right? You're either building it in PSSC, you're putting it in a spreadsheet and you're running a script. You've already done the work to build a disaggregated model. When I was doing it, our script was just, I check a box for both or I check a box for one. And that was the difference of work between the two. So could be a good way. You could also do it in the load flow sense. There are some softwares out there that can do all of it at the same time. I'm not going to advertise for them, but they can do it if you want to find it to do that. And that's basically just a really detailed version of the reactive power study you do at ERCOT plus the scheduled testing, but in the model space. So the other piece that I have opinions on are the voltage or reactive power control modes, which make a lot of sense, right? You want to test the voltage modes. You're gonna, in the North America, you're probably going to be in automatic voltage mode if you're newly interconnecting. So it's very important to test that mode, right? That's the one that's basically on all the time, keeping you within your voltage schedule. It requires you to test all the IBR units, all the supplemental IBR devices. It's a really good test because you test the whole plant's performance at once. The problem here for what's in the new document is we're only picking one mode to test, which the logic for that decision is my transmission service operator is going to say, you're going to operate in AVR mode. Why would I test the other modes? Because I'm never going to operate in them, which is valid for developers, right? The developer, you're not going to go and change your mode unless your operator tells you to, probably. So the perception is I can't change my control mode ever. Why would I ever test the other ones? Well, the answer is other people use your plant sometimes. Maybe there's maintenance and you're in a Q mode, reactive power mode for maintenance. During commissioning, you're in a different control mode. If a neighboring plant is doing a mod test, maybe you're in Q control mode so you don't mess with them. So it's really important to basic, in my opinion, to test any mode your plant could be in. Because it would be, if there's operators or former operators in the room, like it would be awful if you have this plant that works great in AVR mode and I want to take it and put it in Q mode for testing someone else, and then it just starts doing something crazy. They've never validated that control mode. So if you're doing these tests on your side, it's always fine to go above and beyond the standards. There's no maximum effort that we're going to say stop doing work for grid compliance. And testing Q control mode is just probably 3 lines of code in your automation script in 30 extra seconds. Because it's literally just test to make sure you go to a Q set point. It's one of the easiest tests to run and verify. Right? If I put a 10 megabars in my plant controller and I get 10 megabars at the point of interconnection, that's great. If it's wrong, then it's a really easy thing to suss out. So those are 2 major pieces to talk about there. Any questions on reactive power stuff at the POI? Much less contentious, PFR and FFR. You don't need to disaggregate anything, right? The frequency is the same throughout the plant. It's fine to do in positive sequence and EMT modeling because it's aggregated. There's basically no discussion or argument on this one. But the thing to keep in mind is there is a requirement in the design evaluation to show that your plant is doing PFR and FFR right. And again, it won't catch everything, but it's a good check, right? If FFR, AVR is wrong, I'm looking into everything now. There's certain things that you'll notice that you go immediately into check everything mode. So the more complex ones, and this is a little bit of both POM and POC requirements. So voltage disturbance, right through requirements. Both requirements are for at the POM and the POC. So that means basically that the plant must ride through a certain set of parameters, but also the manufacturer, the inverters must ride through. That makes sense, right? And the ways you kind of do this design evaluation, which maybe is important, I should have maybe started with at the beginning, but design evaluation doesn't always mean running a study. It doesn't always mean modeling everything together and running it. You'll see on this table, and I think it's a couple other ones for the more wishy-washy things. You see OEM documentation in there. And that's also okay for some things, right? So if I want to know what the protection settings are for my inverters, you can either take that, put it in your model, just run a bunch of really severe faults and see where things trip off for different voltages, or I can ask the manufacturer and they give me their cut sheet, right? That's fine for OEM documentation. That's also something that should be in the validation report to show you protection operating when it should. So that's what we mean by OEM documentation and capability. That's like the D curve, the reactive power curves. That's your protection settings. That's other things that are clearly written in documentation. And the others are actual modeling. So positive sequence, PSPD, or EMT modeling for the other ones. So for ride through, it's a mix of all three, EMT, positive sequence, and documentations for capabilities. We do also transient overvoltage ride through requirements, which again is very difficult to test and is probably don't adopt that one if you're doing that on your side for now until we revise and fix some of the test procedures. Frequency determinants read through, positive sequence EMT modeling, aggregate model, simple tests that you're all probably doing on your own side already. Returning to service after an IVR trip is also very important for everyone to know how they're coming back and if they're islanding systems for people working on it. For power quality, and I'm not a power quality expert, and you'll see from all the TBDs that we had a hard time filling out this information in the draft just because there aren't that many power quality experts. I believe the final draft has values in here. It was like the last step they did. I just don't remember what they are, and I'm not a power quality expert. But the things they test for those, rapid voltage changes, flickers, harmonic current distortions, harmonic voltage distortions, limitations of instantaneous overvoltage, and limitations of overvoltage over the fundamental frequency period. So some of these are going to be detailed EMT modeling. Some of them might be frequency domain modeling or frequency domain analyses and things like that. So for protection, really going to be pretty darn similar to the PRC for NERC. On the frequency side, I think the values are the same. If they're not the same, they're extremely similar. So very similar tests. You just putting a frequency disturbance on the system, a profile, and you're making sure you don't trip offline. Rate of change of frequency, I believe it would be in addition to what's in the NERC standard, but that's Rokoff. We talked about it yesterday. These types of protections almost never modeled in the PSPD. They're more often modeled in the EMT, if modeled at all, but they're going to be very important. There's a good reason why they're mostly ignored because rate of change of frequency was never super high, but now the grid's weakening, rate Rokoff is going up, and now we see more often those protections actually activating. So testing those, make sure they're doing what they're supposed to do and actually aren't overly constraining is super important. Voltage protection, basically just like PRC 29. AC overcurrent is different, but that's another test you want to run. Oops, based on the parameterization there. Unnatural islanding, interconnection system protection are the other tests that you do for protection. And the last one is modeling data, and that's basically documentation review. That's one of the verified steps of the design evaluation. So checking your modeling data, checking it against OEM documentation, the documentation of the supplemental devices, all of that. So the last kind of check there. So the reality, just to make it clear for the way that where the consensus of the technical experts are, is a little sad for EMT. If you look at the bottom row, right? Because it's so no and maybe and a yes. And quite frankly, the maybe was, man, we fought for that maybe because that was a no for a real long time. You know what? It may actually be a no again. Either way, It'll be published in the spring. But you'll see, right, we're not even in the IEEE standard where, and this is the best practice document that's voluntary, even with the other considerations, even in a voluntary technical consensus standard, we didn't all agree on doing EMT everything. Okay, for the reasons we mentioned yesterday. So really clear, the lines of what we talked about, non-aggregated, no. You're not going to do these tests in a disaggregated EMT model. And there's a subclause in there that explains why, and it's basically what I explained yesterday. There's not a lot of benefit that you don't get in other tools for all of that work and all the computation. Partially aggregated is a maybe, or maybe it's a no. But this is another one of those, really got to think about the trade-off between benefit and computation. Because this is the process of doing maybe your longest feeder, 10, 12 wind turbines plus the aggregated, so 13 plus the plant controller. And that can still be a pretty long simulation. So it's one of those situations where it's a maybe, and even if it's a no, the no, I think, still goes to that subclause in the final version, and it tells you basically some judgment. So to your question earlier, for the aggregation piece, we did put in a subclause, a subclause for how to determine aggregation, if you should aggregate, how you should aggregate, and when. So the kind of note here on the right is the big important one is the non-aggregated stability model may inform proper, oops, that's not that one. In case where the aggregation model provides limited benefit, like we talked about yesterday, so BESS, solar PV, really small plants, aggregate's fine. Just practically speaking, even if there wasn't a control limitation, a computational limitation, aggregate's fine for those types of things. And then I forgot who wrote that note at the bottom, but doing a non-aggregate EMT may be overly burdensome and not provide sufficient value, which is just a firm way of saying use your judgment for what you're doing. All right, so I'm done a little early, probably. Maybe we'll see if I ramble for the next one. But putting everything together, and this is a flow chart that I think is extremely helpful to kind of conceptualize all of this together. And it helps me talk about where this kind of rosy, perfect world design evaluation process butts up against the reality of the world. And one of the key things about IEEE standards is that we're walking a line between informing or providing technical information to be used in requirements without being prescriptive on process, which is extremely hard to delineate when you're having a discussion, because discussion always goes to almost immediately, we should do this thing. And then someone says, well, in my process experience, you can't. And then you're linked to process discussion with this type of discussion. So we try to split it. This would be the, I guess, process agnostic flow chart for doing a design evaluation. As I read through this, keep in mind what your processes might look like, or the ones you're used to working with look like, and then we can rip this apart together at the end. So what's missing here, I guess what's off screen is A. A is the type testing piece. So we're assuming the type testing is done, the data is there. You're taking the type testing data. The first step you're doing is taking the data in A, the unit model from the inverter, and you're validating the model. That's the model validation piece. That's clause 6. If you remember and want to go read through the base standard or the new .2, clause 6, data plus model, validated model. Starting point for everything is a validated unit model and a validated plant control model. This is to be updated, but validated plant control model as well. So you take that validated IBR unit model, you do a model quality test, right? So a model quality test is not design evaluation. I probably should have said that earlier. Model quality tests just never sound really dumb, right? They help you see the quality of the model. And when I say model quality, that's not always accuracy. It's not always performance. Sometimes it's performance. But really it's, here are a bunch of extreme tests to make sure that at the bookends of performance or extreme conditions that the model's not doing anything stupid, like instability in calculations or kind of unexplained rampings or things like that, like a spot check. So it's very similar. And we pulled a lot from ERCOT's model quality process, model quality assessment in the dynamic working group manual. So if anyone has experience using that DWG manual, those tests in there, like the high voltage right through, the low voltage right through, they don't look like real faults, right? They're not it's not a representation of a system fault. The low voltages that fault and then a slow ramp back to 0.90. The high voltages, the profile we all are used to seeing. Faults don't look like that, right? So the point of the model quality test is not to replicate the grid or show grid stability. It's to show that during those crazy extreme events that things aren't breaking. So it's more of like a stress test in the software world than it is a performance test. There are performance requirements sometimes. Once you tested the model qualities, to make sure they're going to work on their own, you put them together like we talked about yesterday. You're developing that verified plant model. You're putting them together, but you're also verifying parameters as you're building the model, like we talked about. Once you build that model, you've got the IVR verified plant model, which includes the validated pieces. So you've got a validated and verified full plant model, which is great, right? So here is where B comes in, because B is kind of helps us have an off ramp or an easier on ramp for accommodating the current process, right? So clauses 6 through, I guess, the top row, that's quite detailed work, right? And you can't do this work until the product's done and built and designed, right? And then it's time after that. So there's often scenarios where if I'm a developer, I might not even know what product I'm using that early in the process. So, or I might know the product I'm using, but it's been pre-sold to me with a brochure from last year and they don't build a model yet for another 2 years. And I don't know how to do it. Or I don't have a model to even run here. So B is the best available plant model, which is like a super broad, very risky thing to say, right? Because that says that if you don't have, or you don't think you have the right model, just use something that you think is the best available, which is a good exemption, but it could also be misused, right? Because I could very easily say, I don't have a UDM, I don't have an EMT, I'm going to use a generic PSPD model for the whole thing, because that's the best thing I have right now. Hopefully that doesn't happen. And to kind of hedge against that, the note here in red is, if you do this, you may need to do the whole thing again, right? Because if you do, if I select the best available model for the first design evaluation, I finish it, and then now the manufacturer has a full type tested validated model, I really should do the design evaluation again with a real model, and do that before commissioning. Because you probably have a model before commissioning. Most of the time, I'm sure there's experience where you don't, but you should have this before commissioning. Got to do the design evaluation before commissioning, because if you don't, then you're just putting an unknown on the system. You're literally putting something you don't know on the system. So that's what the decision point here is. I don't remember what D is, but it's not important. You're selecting the model for your design evaluation. So if I choose the validated model, I'm probably doing it once. If I choose the best available, depending on the quality of my best available, I might do it twice, or maybe 3 times, depending on when I started it and how I'm getting data. So that's when you select it, then you do design evaluation, and it's kind of a little bit recursive here because we're testing and tuning the plant, and nothing ever works right the first time you do it. So this is where you're doing those plant quality tests from the list before, the design evaluation plant level tests. You do the tests. You check those test performance against whatever the performance requirements are and the capability requirements are in the standard. And then you see, well, does it meet the requirements? And again, this is a qualitative assessment, right? So you're looking at the plots, reading the requirements, determining whether or not you met it. If no, then you tune it, you fix it. And this is where it's very important, even if you have a kind of a black box model or a gray box model, that those common tuning parameters are exposed. And that goes to the usability aspect we talked about yesterday. You don't need to see every parameter, but for the things for attribute 2000 and for regular design evaluation that you're testing, like PFR, AVR, those types of things, those are perfectly valid tuning parameters. You're not going to blow anything up by putting the wrong voltage slope in the plant controller. not blow everything up with there. So those are usually things you would tune to test for performance. And then you make that test, you run them all again, and then you check all of them against the conformance. So that's a very important aspect to keep in mind is if you're doing this in the EMT, you're doing this more than once. You're doing all of the tests more than once because you can very easily fix performance for one and make worse performance or lose meeting conformity with the other. So it's this recursive type of testing. It's very similar to the process we talked about in the example yesterday of fixing two contingencies, running the other contingencies to make sure nothing bad happens. So that's design evaluation process and a flow chart with model validation pieces. And I think this is my last one. Yeah, so we're going to take a break a little early. So we'll be back at 10:45. So we'll take a slightly shorter break, but a little early since I'm done and we need to switch to Lucas. And Lucas is going to go through just demos of doing design evaluation, explaining some of those tests. And as he's up here clicking through stuff, I think it would be good just, this is a good opportunity to start asking lots of questions as we go through things you see, and we'll answer them as we go through there. So with that, I'm done talking for the morning, at least until I interrupt Lucas a bunch of times throughout, and we'll see you all again at 10:45.
You said that conformity doesn't ensure. Kind of follows that compliance also. Doesn't principality because standards are based on.
Yep. Yep.
Where does that leave us in terms of liability?
Oh, boy. Very good question. Right. Okay. So we had one final question at the end. And the question was, if conformity doesn't mean grid stability, does that mean compliance doesn't mean grid stability? And the answer is yes. And I'll use an anecdote with maybe a good example of what to do, but it's hard to do it because it requires maybe talking to someone's manager about it and the process. So this happens in ERCOT quite often because of the way, well, one, because they have advanced procedures, and two, because it's a complex system, right? So if you look at the ERCOT's DWG manual and the performance requirements for it, you read things like maximize reactive power response, respond immediately, 90% of your whole response in less than a second. They want a really aggressive, really strong, accurate response. That goes like we saw yesterday, that tuning does not work in a weak grid. Or that tuning might not work in a SSO, SSR situation. So there are many times you will have a situation where I'm going to go, I submit my model through the model quality assessment process. It's perfect. I get a pass. They take that model, put it into the planning case or the interconnection planning case, and there's instability. And then you work with usually that's the utility doing that study. You fixed it for the stability issue. They do the model quality test again because that's part of the process. And now you're failing the model quality test because for a weak grid, I slowed down the gains, right? Or I changed the gains or slowed the response time, which means I missed the requirements in the MQA. So then you either get in a loop and keep doing what everyone says in a vacuum, or you just say, hey, you got to choose which one is right. And this is the problem with region-wide standards with no exemptions, is that you could very easily just get stuck between the two and get delayed, right? Because then ERCOT says no, and utility says no, and then you fix one, and then you go back and forth. So you have to ask, and I've had to have that conversation a bunch of times. And the frank question is just, what do you want? Which is a good answer, a good question, because if you're an IBR, there's a lot of things you can tune to give you exactly what you want. And usually, once you kind of explain the situation, it's easy path forward. So it's like, hey, we show that we could pass the model quality assessment. There's a local stability need we needed to tune around, and that's why we have this. And then you would write that explanation in your model quality assessment. But that's like a small or kind of specific example, but that can happen anywhere. Then a lot of it is just the stability.
Then do we have plans that we just don't know what they're gonna do that are compliant and conforming, that we don't know what they're gonna do until something happens?
Could be.
And isn't that the same place we were 5 years ago with Odessa and all those? I mean, like, it doesn't seem to me like we made any exception. Liability.
Yeah, Lacey, we're gonna cut this next part from the recording. We aren't. We didn't make any progress. Because if you don't have a model quality assessment at the beginning, you're only doing the interconnection studies process. We talked yesterday that generic models used in those processes aren't representing anything. So we don't study them really. And then even if we did study them in a good representation, say we used a full detailed UDM, the other models in the system aren't full detailed UDMs. So a lot of times there's commissioning changes. So even in the perfect world, you're changing at commissioning, and once COD happens, it's a year from mod 26, right? So you literally have a year of nothing. So in a perfect world, even if mod 26 fixes stuff, there's a literal year of unknown operation. And then mod 26 happens, and then you're only testing two simple things: small voltage step, small frequency disturbance. So there are, I mean, all of the plants, all of the plants in the NERC published disturbance reports are NERC compliant, right? They all met mod, they all met PRC, they're all NERC compliant plants. And none of them operated how they should be. So yeah, you're right. Nothing has changed. But the good news is there's, I put in the SAR when I was at NERC, and they gave it to a drafting team for a new standard for FAC 1 and FAC 2, which basically is, we basically copied the table of contents from IEEE 2800 into the SAR. And the process would be not to have a NERC standard that says you must have a voltage requirement with voltage performance of X. It just says you must make a voltage requirement. Just to standardize the types of requirements, requirement categories, I think is the word we use. Because then it still gives freedom to the operators and the planners, but it gives you some guidance for like what you should have. And it's simple stuff like voltage drive through, AVR, PFR, the easier tests for requirements. So that, if you do that at the beginning, during FAC 1, FAC 2, when you have all that leverage, and there's an interconnection requirement based on that, that will close a lot of gap. The problem is that there's none of that right now. And all FAC, for those who do FAC NERC stuff, all FAC 1 says is planners and planning coordinators make a requirement. Simply, you must have all requirement and you must post it online. And then FAC 2 says do studies that meet your requirements. So there's no floor, which means very different processes. And when you have that kind of handoff, it's like NERC doesn't have jurisdiction before COD, and then NERC standards and requirements have implementation times, so you have that year lag, which is bad. Very complex, very visible gaps that we hopefully can close in the next year or two. But even once this is closed, right, even if the standard is done, then it's 2 years ramp into compliance, and then it's probably 3 years after that before the cumulative quality goes up. Then you still have all the old bad models in there. So it'll be even once we fix it on the regulatory side or incentivize it in another way, we're still gonna slowly increase the average quality.
Shop in January of this year. A lot of what you said, what industry brought up in that workshop.
In Phoenix?
Yeah.
Yeah, I was there, yeah.
Same stuff. Here we are almost a year later, talking about the
You wanna know something worse?
same. I don't know if I do.
If you read the recommendations in Blue Cut 2016 and read the recommendations in Odessa 1 and 2, they're almost identical.